So let's continue with electrostatics. We essentially need to work our way through these concepts. Now, we've already talked about charge and Coulomb's law in the Coulomb's law video. So to continue, the idea is that if the object charge actually went missing, we can still pretend that if the object was there, and let's assume the object is positive, that in the presence of another positive charge, it would repel, right? Because sames repel. So in our mind, the concept of electric field is that even with the object missing, you can speak of the field point, a place where the object will be, or is or will be, and the surroundings being the source of electric field. All right, that's not unlike how we treat the weight of an object, mg, where the mass is the mass of the object and little g is the gravity field created by the Earth, which would be the surroundings. So field point, source point. And so, the definition then of electric field is the force that an object would feel if placed at the field point, divided by the object charge, so that the object doesn't disturb the surroundings as well. In the book, it talks about the test charge or object charge being very small. And then next is the idea of electric field lines, right? So if you imagine a positive object or test charge at various places on a plane or in space relative to surroundings, and you think about the force, that then generates a pattern. So for example, if a test object is here and it's positive and here's the source charge, we would repel, right? If an object was placed here, repel, etc. That entire visual pattern is referred to as electric field lines, right? So the electric field is a quantity at a point. Electric field lines is a visual pattern just in our imagination. We imagine the surrounding charge as shooting out electric field lines coming out of positive. If I replace the object, the surroundings, the source, with negative charge, then the electric field lines would come in, right? So electric field relative to source goes away from positive charge or toward negative charge. And so, we get a nice idea here that if, it sort of takes the definition of E, which is the force on an object divided by the object charge, and flip it around and multiply by the object charge and get the force, right? So force is QE. Again, very similar to mg for the weight of an object, right? So there's a property of the system or the object, mass, times this external gravity field, g. In our case, it's a property of the object, its charge, Q0, and this external electric field created by source charge. And that, so this picture here shows red electric field lines such that we don't see what created them, right? We don't see the source. I guess you could imagine that there's positive charges on the left positive charges on the left and or negative charges on the right would cause an electric field line pattern going from left to right. And what the diagram shows is a positive object placed in a field feels a force QE, right? And if Q object is positive, the force would be in the same direction as the field. If the object charge was negative, the negative in the vector formula is like 180 degrees, right? A negative object would feel a force in the opposite direction to the field. So sometimes I roughly say in my mind, positive objects fall down. Now it's to the right, right? Because it's not gravity. And negative objects fall up, right? So positive objects go with the field. Negative objects want to go against the field. The idea of electric flux I discuss a little better in the Gauss's law video. It basically has to do with uh, electric field times area. And there's issues about being sure to get components of the electric field that are actually passing through the area perpendicular to the surface and not components that hug the surface, that are on the surface. But the Gauss's law video does a better job of discussing this. And also Gauss's law, the Gauss's law video goes into this theoretical formula that, or concept that net electric flux associated with a closed surface uh, can only happen if there's charge inside. So again, I'll defer to the Gauss's law video for that discussion. But the important results for us are that Coulomb's law, kq over r squared, again, we're missing the object charge. The smiley face doesn't have to be there, right? That would be the object is missing. But the electric field created by the surroundings. So the results we get from Gauss's law is that Coulomb's law is a direct result of Gauss's law. We also get a similar law like Coulomb's law when there's charge distributions that are spherically that have a spherical symmetry. And again, that's discussed in the Gauss's law video. So the inverse square law is one type of formula that's on exam questions, right? The Coulomb's type problems, whether they be points or spherical symmetry problems. The other main type of problem on tests is where the field is uniform. So if E is a constant, right? In the same way with physics 1 with gravity, you assume that G was everywhere down, right? It was a constant field. So a uniform field, right? E is a constant. And the example of the constant uniform field that's most common in our case is the parallel plate capacitor. That's again discussed in the Gauss's law video. So for the parallel plate capacitor, that's two infinite sheets of charge, equal but opposite charge, and the electric field is confined between those parallel plates, and it's equal to the surface charge density on the positive plate divided by that constant epsilon zero that's introduced in the Gauss law video. The other group of concepts concerns work and energy. Now, as a refresher, people sometimes, you may not remember what is work and what is potential energy. I have a work energy video that goes into this in more detail. But the idea is if an object, now I didn't put the subscript 0 here, if the object is moved from an initial to a final location, if a force is conservative, as the electrostatic force is, there's a change in potential energy. And the potential energy change divided by the object charge is called the change in potential. Now here's a case where we get a new unit, right? Up until now it was all the units from physics 1. But we have now a joule per coulomb actually has its own name. It's called a volt, right? So a change in volts is a change in joules as an object is moved from initial to final divided by its charge. And so to flesh out the rest of the formulas for the two cases we had, the point charge or spherical problems versus the uniform field problems, we have for a point source, kq over r squared, the inverse square law for electric field, and the companion to that for volts. We won't derive that in this video, but it's basically kq over r. Keep in mind also that the electric field is a vector, and so the formulas for the magnitude, that's why the absolute value is shown. Even when not shown, it's implied. But volts, the potential, is a scalar. So if the source charge was negative, we would put the negative in the formula. Unlike for electric field, we would not. We would draw an arrow diagram that's shown by the red arrow. For uniform fields, we get the result that if electric field is constant, essentially the change in volts happens when you travel with the electric field. We get an interesting result that a Newton per coulomb actually is a volt per meter. So the electric field, when uniform, we can just from a change in meters going with or against the field, we can just use the units to get the formula. That's why I have E is the change in volts over the distance moved, either with or against the field. Where it's on you to realize that electric field goes from high to low volts. And I'll say a little more about that when we're live, right? The other way of saying the same thing is the formula in the book. There's a book formula that gives the component in, say, the x direction. You can do this in y or z. But the x component of electric field, if you travel from one point to another, is the negative of the change in volts over the displacement in that direction. So those are equivalent formulas, and I'll have more to say about that when we're together.